Hello guys, so my name is Mohammad Izhaan Khan. Currently, I am pursuing a degree Civil and Environmental Engineering from IIT Patna. So today we are going to start the topic semiconductor devices. Then we'll solve the example questions. So let's see how many questions are there. First one, 40 questions. So maybe 2 sessions will be enough for this. And yeah, let's start now. So the first question is the conductivity of a semiconductor increases with increase in temperature because number density of free current carries increases. Okay, this is option one. Relaxation time increases. Option two. Both number density of carries and relaxation time increases. No. Now option D says that the number density of carries increases, relaxation time decreases, but effect of decrease in relaxation time is much less than increase in number density. So option D is correct. Because see, what happens is in a semiconductor, the conductivity of a semiconductor intrinsic semiconductors I'm talking about. So a number of electrons is equal to number of holes, and now both electron and holes they both contribute to the current conduction. But when some potential difference is applied across like there is a piece of intrinsic semiconductor, then the current flows due to both electron holes and electrons and electron holes. So if I want to write it as a lead current as I due to electrons plus I due to holes. Now this can be written as EANEVE plus NHVH, because current is what? I is equals to V drift velocity E and A. So E and A will be constant because there is the same type of semiconductor, and this part for electrons, this part for holes. So yeah, okay. So now as we know that sigma is equals to J by E, that means I upon AE. Now conductivity of a semiconductor will be sigma is equals to, I'll put I jagah pe A and divided by AE. So it will be E upon E. Yeah, sigma will be E times NE mu E plus NH mu H. This is where V will be the drift velocity, VH will be the drift velocity of holes, and E will be the applied electric field. So mu equal to V upon E. And that is what we have done. Mu is equals to V by E. Alright, mobility of electron, that is called. So in option 4, we have seen that the motion of electrons in the conduction band and of holes in the valence band under the action of electric field, that is happening. So okay, since the number of the number of holes and the number of electrons, that number is increasing so rapidly, that is why the current increases. Alright, so hopping on to the next question now. So the next question says in the figure given alongside V naught is the potential barrier across a PN junction. Alright, when no battery is connected across the junction. Okay, so V naught is the potential barrier when across a PN junction. When no battery is connected across the junction, 1 and 3 both correspond to forward bias of junction. 3 corresponds to forward bias, 1 corresponds to reverse bias. 1 corresponds to forward bias, 3 corresponds to reverse bias, and the option 4, that is obviously wrong. So the key concept behind this is, in a PN junction diode, when a P-type semiconductor is suitably joined to an N-type semiconductor, then that's the arrangement that we know is the PN junction diode. What is the depletion region in this? So I'll just draw it over here. P and then P N. Okay. This is anode and this is cathode. Alright. So the depletion region is the on account of difference in concentration of charge carriers in the two junctions of the, like there's a P junction and N junction. So the electrons from the N region diffuse through the junction into P region. I'll draw it over here. Like this happens. I'll show you. This is a PN junction. This is the P type. This is the N type. So what happens is electron and holes get interchanged like this. Okay. So the depletion layer can be shown as this with a better diagram. This is the plus, 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 plus. Alright. This is the junction. Minus, minus, plus, plus, and minus, 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 minus. This is the n type. Okay. Since the electron flowed from here to here, the holes that were here were filled by an electron, and the consequence was the electrons which moved from the n type created holes in the n type. So there's a plus side over here. So the thickness of the depletion region is in micron. Okay, so the width of this depletion layer, the width that it has, W. W is inversely proportional to the doping. Okay, so depletion is this depletion width W is directly proportional to temperature. That is also important. It is directly proportional to temperature. And the PN junction diode is equivalent to a capacitor in which the depletion layer that is there, it will act as a dielectric. So which option is correct? Option number B. 3 corresponds to forward bias of junction and 1 corresponds to the reverse bias of junction, because the potential is increasing when we are going on a reverse bias. So that is correct. Moving on to the next question now. Question number 3. Assuming the diodes to be ideal, D1 and D2, D1 is forward biased and D2 is reverse biased. Hence, current flows from A to B. D2 is forward biased and D1 is reverse biased, and hence no current flows from B to A and vice versa. D1 and D2 are both forward biased, and hence current flows from A to B. And D1 and D2 are both reverse biased, and hence no current flows from A to B and vice versa. Okay, so let's see. So a symbol we already know. Okay, if the current flows like this, it is a forward bias condition. First we'll go through P and then we'll encounter X. Okay, but if you will want the current to flow like this, the diode is like this from N to P, and you put a current I over here, then it will just break the circuit like this. Okay, so this will happen in this case. So this is a simple like diagram of this diode. So if we see, so at point A, we are seeing a minus 10 volt. Okay, now let me just draw the circuit that they have given to us. This is minus 10 volts. All right. There's a resistance R. There's a diode D1, and there's a diode D2, and then we have what? A thing that is grounded. So we already know at ground potential is 0. So this potential at B and this potential at, let's say, A, VA. VB is greater than VA. So this is at high potential. So this is the way that current will flow. So this D2 will be forward biased first of all. Okay, so in option B it is given D2 is forward biased and D1 is reverse biased. Hence no current flows from B to A and vice versa. Absolutely correct. See, the current wants to flow like this due to the potential difference. Alright, VB is at a higher potential than VA. Now the current wanted to flow from B to A. And when it encountered B2, it found it is forward bias, so it just flowed like this. But when it went to D1, then the N type was before the P type. So what happens is it will act as the circuit has been broken down till this part. So that is why no current will flow. Okay. Now moving on to the next part. A 220 volt AC supply is connected between the points A and B. What will be the potential difference V across the capacitor? Okay, so there's a 220 volt AC supply connected between the points A and B. What will be the potential difference V across the capacitor? Okay, so let's see. So since that is an AC supply and the options have been given, so we'll just calculate it for it. So when let's see this. Since it is an AC supply and the diode has been given to us, is a capacitor. Okay, so in 1 unit of time, the potential is like this. So the current wants to flow like this. In another unit of time, the potential is just like this. The current wants to flow like this. But tell me, can the current flow if the current is moving like this? Can the current flow through the circuit? No, because the diode will be in the reverse bias condition and it will break the circuit. So this current will not flow. Only this current will flow. So I'll just make a circuit out of it. Yeah, like this. Okay. And this will be my potential. So I'll draw it again over here. 220 volt AC supply. There's a and capacitor over here. Okay. So what is happening? What do we have to tell? We have to potential difference across the capacitor. We will have to tell about the peak value, na? So what will be the peak value for this? Tell me. Peak value is V naught is V root mean square का under root 2 है ना? And VRMS has been already given to us as 220. So this will be the answer V naught. Itna potential will be released from over here. No potential drop will be across this diode because it will act as a closed circuit just like this. Okay. Now when it will reach here, the potential drop against this capacitor will be equal to the potential that has been given by this source. So what will be that value? It will be VRMS multiplied by under root 2. So V naught under root 2 will be the value. 220 under root 2 will be the correct answer for this. That will be option 4. Hole is an antiparticle of electron, a vacancy created when an electron leaves a covalent bond, absence of free electrons, and artificially created particle. Okay, so let me tell you one thing. What if you read about this question, you will be thinking about option A, B, C as the most valid ones. But the reality is that option D is the correct answer for this. That holes are an artificially created particle. Why? See, the concept of holes that are in the semiconductor is that when an electron is removed from a covalent bond, it leaves a vacancy behind. So, an electron from a neighboring atom can move into this vacancy, leaving the neighbor with a vacancy. So, in this way, the vacancy is formed. Now, this vacancy, we have artificially named it as a hole, and we have given it a significance in our studies. Just to understand that where the electron will move, we have made this concept of holes. Okay, so that hole is considered as a seat of positive charge because there is a vacancy of electron over there. So we consider that there is a positive charge, like a plus sign over there, because there is a vacancy of electron. You are getting my point. So this holds, these act as a virtual charge. Although there is no physical charge on it, there is no actual positive charge on these holes. We just assume that there is a plus sign over there because there is a vacancy of electrons. Now, one more thing: effective mass of hole is more than an electron. Okay. Mobility of hole is also less than that of electron. So these are some few points, but this option is correct. We have made this concept of holes just to understand the study of these semiconductor easy. Alright. Moving on to the next question. Okay. The output of the given circuit would be 0 at all times. Would be like a half wave rectifier with positive cycles in output. Would be like a half wave rectifier with negative cycles in output. Would be like that of a full wave rectifier. Okay. So now this is the input voltage V. Alright. So this is the input voltage V with time T. What will happen is there's a diode, since there's a diode over here, it will just allow one part of this voltage to flow like this. Alright. During the half cycle, diode will be forward biased, so it will let the current flow like this, just like the same concept we had done in the last previous one. So when the diode is forward biased during positive half cycle of input AC voltage, the resistance of PN junction that will be low and the current will pass through the circuit. The current that will be passing will be the maximum. So in this situation, the maximum potential difference, which will be what VRMS under root 2. Okay. The maximum potential difference will appear across the resistance connected in a series of circuits. So the result into our zero output voltage across the PN junction will be there. And when the diode will be in the reverse bias condition, the negative half cycle of AC voltage that I showed now, that the circuit will break on that point where the diode has been put in the reverse bias condition. That will break the circuit and the negative cycle of the potential will not flow through. Okay, the resistance of PN junction becomes high, which will be more than resistance in series. That is why there will be voltage across PN junction with negative cycle in output. Hence, the option C will be the correct answer. Would be like a half wave rectifier with negative cycles in output. Okay. So now moving on to question number 7 now. So in the circuit shown in figure 14.5, if the diode is forward voltage drop is 0.3 volts, the voltage difference between A and B is what? Okay. So the circuit has been given to us. Let us just draw it. point A. So 5 kilo ohm resistance over here. Okay, a capacitor going over here, a diode over here, a 5 kilo ohm resistance again, and then we have point B. Okay, so what has been given in the question is there's a 0.2 milliampere current, 5 kilo ohm over here, 0.3 volt. Okay, 5 kilo ohm over here. So that has been given to us already. Voltage drop between the diode is 0.3 volt. Alright. So the voltage difference between A and B will be what? It is a very simple question actually. Okay. Now since the diode is in a forward bias condition, okay, we'll assume the potential difference only, and we'll think of the diode as a straight wire, but there will be a potential drop or potential gain. We'll see how the diode has been put. Alright. So now let us consider that the current that has been flowing is uniform. Okay. Now I'll just write it over here. VAB minus 0.3. Okay, this 0.3 has been lost in this potential run. So this will be equal to R1 plus R2, like what was it? 10 kilo into 10 raised to the power of 3 into the current that has been flowing is 0.2 into 10 raised to the power of minus 3. Since the circuit has been not closed over here, why will the current go in this direction? Like, it's absurd to think like that. And also, this is a capacitor over here, alright? So VAV minus 0.3 will be equal to 10 into 10 raised to the power of 3, alright, kilo into 0.2 into 10 raised to the power of minus 3. So here will be 2. So VAB, V across AB will be 2.3 volts. Okay, that will be the correct answer of this. Moving on to the next question, the truth table for the given circuit that has been given to us is like this. Okay, now we'll just have to check it one by one. I write it over here. Okay, first of all, it will be A, B, A dash, C is equals to AB. See, A went over here, B. So A and B. Okay, that will be C. Okay, it is correct. Now D. D will be what? A dash into B. Okay, so D will be A dash B. And finally, E will be equal to C plus D. Now E will be C plus D. Alright, so now we'll just start. So A will be for 0, 0, then 0, 1, and 1, 0, and 1, 1. So A dash will be what? A dash will be 0 to 1, 0 to 1, 1 to 0, 1 to 0. Okay. Now C is A into B. A into B is A and B, and 0, again 0, again 0, now 1. D is A dash B. So A dash B is what? 0, now 1, 0, again 0. E is C plus D. C plus D and B. Or. Okay. Or it is. So 0, 0 will be 0, 0, 1 will be 1, 0, 0 will be 0, 1, 0 will be 1. This is the or the procedure. So we have found the values for E, 0, 1, 0, 1. Now we'll just match it with the truth table. They've arranged the truth table as 0, 0, and like what have they done? They've arranged it differently. Okay. So we'll just check for when A is 0, 0, EQ value is 0. A is 0, 0, EQ value is 0. Now we'll just have to check between these two. So at 0, 1, 0, 1, the value is 1. 0, 1 पे value 1, 0, 1 पे value 1. 1, 0 पे value 1, 0, the value is 0. 1, 0, value is 0. 0, 1, 0, 1. This one is correct. Okay. So option C is the correct answer. When an electron field is applied across a semiconductor, electron moves from lower energy level to higher energy level in the conduction band. Electrons move from a higher energy level to lower energy level in the conduction band. Holes in the valence band move from a higher energy level to lower energy level. Holes in the valence band moves from lower energy to higher energy. Okay, let's check. So when an electric field is applied across a semiconductor, so option A is correct. Electrons move from lower energy level to a higher energy level in the conduction band. Okay. And since it is a multi-correct type, more options will be good. So electrons move from higher energy to lower energy. That is obviously wrong because it contradicts our option A. Now option C, holes in the valence band moves from higher energy level to lower energy level. Holes, yeah, obviously correct. So since the electrons, see what is happening, electrons and holes are complementary. Yeah. See, this is the valence band. Now, what will happen is, so there was an electron over here. Oh, sorry. There are electrons over here, electron over here, electron over here. When this electron will jump to a higher energy level and reach this point, there will be a hole in this position. Now, I'm assuming that there was an electron over here. It reached from this point, leaving behind a hole. So this hole, there's originally a hole over here because there's an absence of electrons. When this electron will reach this point, it will be consumed by an electron, and this will be consumed by an hole. So the holes are moving down, electrons are moving up. All right, simple. So holes in the valence band move from a higher energy to lower energy. Since the electrons move from a lower energy to a higher energy in the induction band, obviously. So now we'll move on to the next question, which is on NPN transistors. Okay. So we have to consider an NPN transistor with base emitter junction forward biased and collector base junction reverse biased. So which of the following statements will be true? No. So in normal operation, base emitter BE, that is forward biased, and the positive pole of emitter base battery is connected to the base and its negative pole is connected to the emitter. Okay, now if you want me to draw, I'll draw it for you. What happens is, okay, this is the emitter E. Okay, this is the plate. This moves like this. Here it goes to C and the base goes to B. Alright. So E, C, B we already know. E is the emitter, C is the collector, and B is the base. So now in normal operation, base emitter is forward biased. So that we already know. Collector base junction is reverse biased. The positive pole of the collector base battery is connected to collector and negative pole to base. This electron moves from the emitter to base and crossover from emitter to collector. So option A says that the electron crossover from emitter to collector, that is true. And B, holes move from base to collector, that is wrong. C, electrons move from emitter to base, that is correct. So option A and C are correct. Okay, option A and C are correct for question number 10. Now moving on to question number 11. The figure given alongside shows that transfer characteristics of a base bias CE transistor. Which of the following statements are true? At Vi equal to 0.4 volt transistor is in active state. At Vi is equals to 1 volt. It can be used as an amplifier. At Vi equal to 0.5 volt, it can be used as a switch as a turned off. At Vi equal to 2.5, it can be used as a switch turned on. Okay, so according to the above graph, transfer characteristics of a base biased common emitter transistor has been given to us. Now we can note that when the voltage is 0.5 volt, okay, so it will be in this region, right? 0.4 volt. So 0.4, yeah, it will be in this region. So output voltage remains same. There is no collection current. So transistor circuit is not in the active state. So option A is wrong. It is not in the active state right now. When Vi equal to 1 volt, that is between 0.6 to 0.2 volt in this region. Okay, the transistor circuit is in the active state, and when the input is increasing, output is increasing. Okay, so this can act as an amplifier. Okay, voltages are 180-degree out of phase, so this acts as an amplifier. So option B is correct for now. In option C, when V equal to 0.5 volt, just before this, or like there is no collector current, the transistor is in the cutoff state. Okay, yeah, this is also true. It can act as a switch, as a turned off switch. Option C is also correct. And option C, at Vi equal to 2.5 volt, this is obviously an open circuit condition, so it can act as a switch that has been turned on. Okay. So moving forward, in a NPN transistor circuit, the collector current is 10 milliampere. If 95% of the electrons emitted reach the collector, which of the following statements are true? Alright. The emitter current will be 8 milliampere, the emitter current will be 10.53 milliampere, the base current will be 0.53 milliampere, and the base current will be 2 milliampere. Okay, since there is an NPN transistor circuit, option B, the emitter current will be, let's just calculate for it. So since I is the emitter current, I will say that IE is my emitter current, alright, IC is equals to 95 upon 100 IE. Alright, now this IE is equals to 10 into 100 upon 95. So it will be 10.53 milliampere. Okay. Also, what happens? IB plus IC is equals to IE, right? Now, IB is IE minus IC. So 10.53 minus 10. So it is equals to 0.53 milliampere. So option C, the base current will be 0.53 milliampere is correct. And option B, the emitter current will be 10.53 milliampere is also correct. Okay. So option B and option C are correct for this question. Now, question number 13th. So, in the depletion region of a diode, there are no mobile charges. Equal number of holes and electrons exist, making the region neutral. The combination of holes and electrons has taken place, and immobile charge ions exist. So, on account of difference in the concentration of charge carrier in two sections of P and junction, the electrons from the N region, the electrons that are there in the N region will diffuse through the junction into the P region, and the hole from the P region diffuses into the N region. So just draw a diagram over here for you to understand. See, this is the junction actually. All right. Now, this is a positive, 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 positive. All right. This is a negative, 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 negative. All right. What was there initially? There was a positive charge over here, right? There's a negative charge over here. Positive, negative, positive, negative, positive, negative. What happens was this electron moved from here to here. Alright, creating a hole over here. This electron moved from here to here, creating a hole. An electron moved from here to consume a hole and created a hole consequently. Okay. So now, mobile charges are there or not? Tell me this. A. No mobile charges, which is absolutely correct. Why? Because see, these are not mobile charges. They cannot go freely around in this whole thing. They are just like transfers due to the potential difference. Okay, there was an initial like you read a 0.6 volt, 0.8 volt. That is the difference, potential difference that is being generated between this depletion layer. Okay, so these are not free charges. So these are not mobile charges. Option number B: equal number of holes and electrons exist, making the region neutral. Equal number of holes and electrons. That is also correct. Equal number will be there. The combination of holes and electrons is taking place. That is option C. No, that is not true. Holes and electrons, the recombination that has not been taking place. The electrons move from their position, and as a consequence, the hole was created. Okay, they did not recombine or something like that. Immobile charges, immobile charged ions exist. That is option number D. Immobile charged ions exist. That is also true. These charged ions are immobile. Okay. So due to the diffusion, neutrality of both N and P type semiconductor is disturbed. Okay. So a layer of negative charged ions appear near the junction in the P crystal, and a layer of positive charged ions appear near the junction on the N crystal. This layer is called the depletion layer. The thickness of this depletion layer is in the micron region, and the width of this depletion layer is, I already told you, inversely proportional to 2 pi. Now, depletion is directly proportional to temperature, and the important point is the PN junction diode is equivalent to the capacitor in which the depletion layer acts as a dielectric. So these are the 3 points that you'll always like recall whenever you come through this situation. All right. So just a moment. So now we're talking about the Zener diode. So what happens during regulation action of a Zener diode? Okay. Option A, Zener diode. First of all, you should know how it looks like. Beautiful. So the current and voltage across the Zener remains fixed. Wrong. The current through the series resistance RS changes. Correct. Okay. The Zener resistance is constant. Wrong. The resistance offered by the Zener changes. So option B and option D are correct. Okay. So this Zener is represented like this. In the forward bias condition, the Zener diode will act as an ordinary diode. It can be used as a voltage regulator. Okay, first of all, this is important one. A Zener diode, when in the reverse bias condition, will offer a constant voltage drop across in terminals as unregulated voltage. Okay, so then during regulation action of a Zener diode, the current through the series resistance RS will change, and the resistance offered by the Zener also changes. So the current through the Zener changes, but the voltage across the Zener remains the same. So option B and option D are correct for this. Okay, now we have what? To reduce the ripples in the rectifier circuit with capacitor filter, RL should be increased, input frequency should be increased, capacitor with high capacitance should be used. Okay, so we'll see about this. So the ripple factor may be defined as the ratio of the RMS value of the ripple voltage to the absolute value of the DC component of the output voltage. Alright. So it is usually like however this ripple voltage is commonly expressed as the peak to peak value. Ripple factor R of a full wave rectifier. Okay, I just write it over in 0.236 R upon omega L. Okay, where L is inductance of the coil, omega is the angular frequency or ripple factor. Okay, now this R can be written as 1 upon 4 under root 3 V R L C P. So this R is inversely proportional to 1 upon RL, and R is inversely proportional to 1 upon C. R is inversely proportional to 1 upon B. So the ripple factor is inversely proportional to RL, C, and B. Okay, ripple factor R is inversely proportional to all three of these. Thus, to reduce R, RL should be increased, input frequency V should be increased, and capacitance C should be increased. So option A, RL should be increased, is correct. Option B, input frequency should be decreased, is wrong. Option C, input frequency should be increased, is correct. And option D, capacitors with high capacitance should be used. So option A, C, D are correct. Okay, so now we have question number 16th. So the breakdown in a reverse biased PN junction diode is more likely to occur due to the following reasons are given to us. The breakdown in a reverse biased PN junction is more likely to occur due to large velocity of the minority charge carriers if the doping concentration is small, large velocity of the minority charge carriers if the doping concentration is large, strong electric field in a depletion region if the doping concentration is small, and strong electric field in the depletion region if the doping concentration is large. Okay. So in the reverse biasing condition, positive terminal of the battery is connected to the N crystal and negative terminal is connected to the P crystal. Alright. So in the reverse biasing condition, we already know that the width of the depletion layer will increase, and this in reverse biasing resistance will be great. So our reverse can be written as something. The breakdown of the reverse biased P junction is more likely to the breakdown. We are talking about the breakdown. Okay. So breakdown voltage, that will be the reverse voltage at which the breakdown of the semiconductor will occur. Yes, correct. Okay. So we conclude that in reverse biasing, ionization takes place because the minority charge carriers will be there, and it will be accelerated due to the reverse biasing, and it will strike the atoms, which in turn cause secondary electrons, and thus more number of charge carriers will be there. And when doping concentration is large, there will be a large number of ions in the depletion region, which will give rise to a very strong electric field. So that will cause the breakdown voltage. See, it is like when you draw this diagram, when you go back, this is the reverse current. Okay, reverse current. See, if it is I, obviously it will be minus I reverse current, and it will be reverse voltage over here. So that will be reverse voltage. So a breakdown has occurred over here. This is called a breakdown voltage. So option A, large velocity of the minority charge carriers if the doping concentration is small, A is correct. And option D, strong electric field in the depletion region if the doping concentration is large, that is also correct. So option A is correct and option D is correct. So now VSA. Why are elemental dopants for silicon or germanium usually chosen from group 13 or group 15? When pure semiconductor material is mixed with small amounts of certain specific impurities with valency different from that of the parent material, the number of mobile electrons or holes drastically changes. So the process of addition of impurity, this process is called doping. Now the size of the dopant atom should be compatible such that their presence in the pure semiconductor, like that if the size is compatible to the atoms of the semiconductor. It will not destroy the semiconductor, but it will easily contribute to the charge carriers. Okay, so this covalent bond will be formed with either silicon or germanium atoms, so which are provided by group 13 or group 15 elements. Basically, you have to remember one thing: the size should be compatible. The valency difference should be there. Okay, if the size is not compatible, then it will just it will not be that efficient. All right. So this has been found in silicon and germanium, which are in group 13 and group 15 of the periodic table, respectively. And now, for this reason, these groups are preferred over others. So now, tin, carbon, and silicon, germanium are all group 14 elements. Yet, tin is a conductor, carbon is an insulator, while silicon and germanium are semiconductors. Why? Okay. So, in order to answer this, we have to talk about the conduction level of any element. So, this conduction level will depend on the energy gap between its conduction band and valence band. So, in the conductors, there is no energy gap between the conduction band and valence band. And for insulator, the energy gap is large, and for semiconductor, the energy gap is moderate. I'll draw it over here. Okay, I'm drawing the valence band. So, this is for insulators. Insulators. Okay, bring it a little closer. This is for semiconductor, and finally, this is for conductor. Alright. So the energy gap for tin is 0 electron volt, and for data wise, I'm telling you, for carbon it is 5.4 electron volt, and for silicon it is 1.1 electron volt. So when the difference between the energy gap between the valence the bands is like extremely large, like it has been given 5.4 electron volt for carbon, then it will obviously not conduct the electrons. When it is moderate, like 1.1 electron volt, it can act as a semiconductor. And for conduction, conductor is tin, it is 0 electron volt, so it will easily let the electron pass through it. Now draw the output waveform across the resistor. Okay, V naught है pi plus 101 waveform. The diode will act as a half wave rectifier. It offers low resistance. Okay, it will act as a half wave rectifier. That is the 0 line. This is the minus line. Okay, I'll draw it for you. See, this is the full wave. Okay, this is the minus 1 point. This is the minus 1 volt time. This is the 0 point, and this is the line for 1 volt. Now it will act as a half wave rectifier. So it will cancel all the negative voltages. So they will be, this will be my 0, this will be my plus 1. और नीचे का part गायब. This part is no more. Okay, so this will be the correct waveform. Now hopping on to question number 21. The amplifiers X, Y, and Z are connected in series. If the voltage gains of X, Y, and Z are 10, 20, and 30 respectively, and the input signal is 1 millivolt peak value, then what is the output signal voltage? Okay, so if DC supply voltage is 10 volt, if DC supply voltage is 5 volt. Okay, now the total voltage amplification will be defined as the ratio of the output signal voltage and the input signal voltage. Now, according to the problem, the voltage gain in X, Vx is equals to 10 volt. The voltage gain in Y, Vy is 20 volts, and the voltage gain in Z, Vz is 30 volt, and delta Vi is 1 millivolt, that is 10 minus 3 volt, and total voltage amplification will be Vx, Vy, Vz into delta V. Okay, total voltage amplification will be there. It will be Vx into Vy into Vz into delta V. So multiplying all these things together, so it will be 6 into 10 to the power of 3 into 10 to the power of minus 3. So it will be 6 volts. Alright, this is the total voltage amplification. Now, if DC supply voltage is 10 volt, then output is 6 volt, since theoretically gain is equal to the practical gain. So output can never be greater than 6 volt. And in option 2, if DC supply voltage is 5 volt, so VCC is equals to 5 volt, then output will not exceed 5 volt. Then V naught will be equal to 5 volt only. In question number 22, in a CE transistor amplifier, there is a current and voltage gain associated with the circuit. In other words, there is a power gain. Considering power a measure of energy, does the circuit violate conservation of energy? So different gain in C transistor amplifier. Current gain beta has been given to us. Okay, the current gain beta, it is delta IC on delta IH. Okay, current gain BDC will be IC upon IB. Voltage gain is also there. So the power gain is very high in CE transistor amplifier only. So in this circuit, the extra power required for amplified output is obtained from DC source. Thus, the circuit used does not violate the law of conservation. Okay. See, power gain is what? Power gain. It is equals to beta square AC into resistance gain. Alright. So now the extra power that is required for amplified output that is obtained from the DC source. Okay. So there is no violation of conservation of energy. Okay. Short answer type questions. Name the type of a diode whose characteristics are shown in figure A and figure B. Okay. And what does the point P in figure A represent? That is the breakdown. Okay. We'll check it. What does the point P and Q in figure B represent? Alright. So we'll go. So now the figure A, it is representing the characteristics of a Zener diode. Okay. And curve B is of the solar cell. Okay. So A represents what? Zener, and B represents solar cell. Alright. Now, in figure A, the point B in the Zener is the breakdown voltage. Alright. And in the figure B, the point Q represents zero voltage and negative current, which means the light falling on solar cell with least minimum threshold frequency will give the current in opposite direction to that due to the battery connected to solar cell. But for that point Q, the battery is short circuited, hence it represents the short circuit current. And the point in the figure B, the other point P, it is representing the open circuit. So voltage is there, but the current is zero through the solar cell. It means there is a battery connected to a solar cell which gives rise to equal and opposite current to that in solar cell by virtue of light falling on it. On it. Now we have question number 24. So three photodiodes C1D2 is having band gaps of 5 electron, 2 electron, which ones will be able to detect light wavelength 6000 angstroms. Okay, so we'll check. Photodiode electrons in voltage of we can just solve it by that. Equals to 6000 to 10 raised to the power of minus 10 meters. So energy that is being falling on it will be 6.6 into 10 raised to the power of minus 34 H into C3 into 10 raised to the power of 8 meter per second divided by lambda that is being given to us as 6000 into 10 raised to the power of minus 10 into 1.6 into 10 raised to the power of minus 19 whole electron volt. Let's calculate it. Okay, 2.0625 electron volts. Okay, 2.0625 electron volts. So I can write it as 2.0625 electron volts. So the incident radiation, which is detected by the photodiode D2, because energy gap of incident radiation is greater than the band gap is there. Moving on to question number 25. If the resistance RL is increased, how will the readings of the ammeter and the voltmeter will change? So let us see. First of all, the base current IB will be equal to VBB minus VPE. What is VBE? The potential difference in this part, VBE. Okay, divided by RL. So this IB is inversely proportional to 1 upon RL. So R1 is increased as IB is decreased. Now the current in the ammeter is the collector current IC. IC is equals to beta times IB. IB is decreased. IC is also decreased. And the reading of the voltmeter and ammeter is also decreased in this case. So we'll start from the question number 26 in our next class. And you can solve these questions all by yourselves before coming to the next class and check it. Like if you're like you have seen the solution first, so that is basically a problem when you are learning a new concept. But still, it's okay. You can redo these questions again, and this time try to do it on yourselves. Okay, if you get stuck anywhere, then you can come back and refer to this video solution. Alright, so see you in the next class. Bye bye.